Hey guys, welcome to this new story. Today, we turn our attention to one of the greatest mysteries in the universe, dark matter. This invisible substance makes up most of the matter in the cosmos, yet it cannot be seen, touched, or directly measured. Its presence is known only through the way galaxies rotate, how clusters of stars hold together, and the bending of light across vast distances. But what is dark matter really? Why does it dominate the universe while remaining completely hidden from our instruments? How does it shape the galaxies, stars, and cosmic structures we can observe? Scientists have devised experiments deep underground, in space, and with particle detectors, searching for clues that might reveal its nature. In this video, we explore what we truly know and what we are still learning about the invisible force that holds the universe together. The existence of dark matter was first suggested in the early 20th century when astronomers observed motions of stars within galaxies that could not be explained by the visible matter present. In 1933, Fritz Zwicky measured the velocities of galaxies in the Coma cluster and found that the mass inferred from their motion far exceeded the mass that could be accounted for by luminous material. This discrepancy suggested that most of the matter in the cluster was invisible. Over the decades, similar observations accumulated, revealing that the gravitational effects of unseen mass were common throughout the universe. Galaxies did not rotate according to the distribution of stars alone, and clusters of galaxies exhibited gravitational binding that could not be explained by visible mass. The term dark matter was adopted to describe this component of the cosmos that interacts through gravity but emits no light. It became clear that this invisible mass was not just an anomaly in isolated cases, but a fundamental feature of the universe's structure. Observations of galaxy rotation curves provided one of the most compelling early pieces of evidence for dark matter. In a galaxy, stars orbit the center under the influence of gravity. If only visible matter contributed to the mass, stars further from the center would orbit more slowly than those closer in, following a predictable decline in velocity. Instead, astronomers found that stars at the edges of galaxies moved at speeds comparable to those near the center. This flat rotation profile suggested the presence of additional mass beyond what could be seen. The inference was that a halo of unseen matter surrounded the luminous portion of the galaxy, extending well beyond the visible disk. This halo would account for the observed rotational velocities, ensuring that stars remained bound to the galaxy rather than drifting into intergalactic space. Clusters of galaxies further reinforced the evidence. The motion of galaxies within these clusters showed that their combined mass must be much greater than what could be measured from visible stars and gas alone. X-ray observations of the hot gas in clusters revealed temperatures too high to be held by the gravity of visible matter alone, implying an additional gravitational source. Gravitational lensing, the bending of light from distant background objects by massive foreground clusters, provided another method to map the mass distribution. Lens observations consistently indicated mass concentrations far exceeding that of luminous matter. In multiple cases, including well-known clusters such as the Bullet cluster, the separation between visible matter and gravitational mass revealed a component that interacts primarily through gravity and not through light or electromagnetic radiation. Dark matter is not composed of ordinary baryonic matter. Ordinary matter consists of protons, neutrons, and electrons, and it emits or absorbs electromagnetic radiation. Dark matter does not interact in this way, making it invisible across the entire spectrum of light. Its presence is inferred solely through gravitational effects. Despite decades of research, no experiment has yet detected direct interaction between dark matter and ordinary matter beyond gravitational influence. Its elusive nature has led to extensive theoretical work to propose candidate particles and models that could account for its properties while remaining consistent with observations of cosmic structures, galaxy dynamics, and the evolution of the universe. The cosmological significance of dark matter extends to the large scale structure of the universe. Simulations of galaxy formation require a significant proportion of dark matter to match the observed distribution of galaxies, filaments, and voids. The earliest density fluctuations in the primordial universe would collapse under gravity more efficiently with dark matter present, leading to the formation of galaxies and clusters in the patterns observed today. Without this additional mass component, the universe would appear less structured, and the distribution of galaxies would be inconsistent with what is seen in surveys. Dark matter provides the gravitational scaffolding for cosmic architecture, shaping the universe on scales far beyond individual galaxies. Efforts to quantify the total amount of dark matter indicate that it constitutes approximately 27% of the total energy matter content of the universe. Ordinary matter accounts for only about 5%, with the remainder composed of dark energy, a distinct phenomenon driving cosmic acceleration. These proportions are derived from multiple sources of observational data, including the cosmic microwave background, supernova distance measurements, and the distribution of galaxies on large scales. Together, these lines of evidence converge to paint a consistent picture of a universe dominated by unseen mass, which governs the behavior of visible structures through its gravitational influence. The discovery and study of dark matter illustrate the interplay between observation and theory in modern cosmology. Observational anomalies prompted the development of new models and hypotheses to explain the unseen component. The concept evolved from initial measurements of galaxy velocities to detailed simulations of structure formation, and it continues to challenge our understanding of the fundamental composition of the cosmos. Researchers also use a combination of observational astronomy, particle physics, and theoretical modeling to explore its properties, continuously refining predictions and testing them against empirical data. This process underscores the rigor of scientific investigation in confronting phenomena that cannot be directly observed but whose influence is undeniable. Over the 20th and 21st centuries, advances in instrumentation and methodology allowed increasingly precise measurements. Large surveys, such as the Sloan Digital Sky Survey, mapped the positions and velocities of millions of galaxies, revealing patterns consistent with a pervasive dark matter component. Observations of gravitational lensing around clusters and individual galaxies have enabled detailed reconstructions of dark matter distributions. Complementary measurements of the cosmic microwave background provide insight into the early universe, showing that the seeds of cosmic structure formed in the presence of dark matter. Together, these datasets form a converging body of evidence that dark matter is a major, quantifiable component of the universe. Dark matter remains invisible, yet its effects can be studied indirectly with precision. The stability of galaxy clusters, the rotation of galaxies, and the bending of light all serve as tracers for its presence. These effects provide information about its distribution, density, and interaction with ordinary matter. Theoretical models must account not only for these gravitational phenomena, but also for consistency with particle physics, cosmology, and high-energy astrophysics. Research continues to explore how dark matter contributes to galaxy formation, how it influences large-scale cosmic flows, and how it might interact, if at all, with forces beyond gravity. The persistence of dark matter as an unsolved problem highlights the limits of observational knowledge. While its gravitational influence is measurable, its particle identity remains uncertain. Experiments in underground laboratories, high-energy particle collisions, and astrophysical surveys seek to detect direct or indirect signals of dark matter particles. Each method has set increasingly stringent limits on the properties and interactions of candidate particles, narrowing the parameter space for viable theories. Despite these efforts, dark matter has proven resilient to direct detection, maintaining its role as one of the most significant mysteries in contemporary physics and cosmology. The conceptual framework of dark matter integrates multiple disciplines. Astronomy provides measurements of mass distributions and motions. Particle physics proposes possible constituents, while cosmology models the universe's evolution under different assumptions about matter composition. This interdisciplinary approach has produced robust predictions and frameworks guiding observation and experiment. The presence of dark matter is no longer speculative. It is a critical element in understanding the universe's structure and dynamics. Its study exemplifies the ongoing dialogue between data and theory, each informing and refining the other in the pursuit of knowledge. Galaxies are collections of stars, gas, dust, and dark matter held together by gravity. Observing their rotation provides insight into the distribution of mass within them. In a galaxy, stars orbit the center, moving in paths determined by the gravitational pull of the mass inside their orbits. When astronomers measure the rotational speed of stars at different distances from the center, they can infer how mass is spread throughout the galaxy. In the simplest case, where only visible matter exists, the rotational velocity would decrease with distance from the center. Stars far from the galactic core would move more slowly, reflecting the declining gravitational influence of the luminous matter in the inner regions. This expected pattern mirrors the way planets orbit stars in a solar system, where the Sun contains most of the mass. Early observations, however, showed a different reality. In the 1970s, Vera Rubin and her colleagues measured the rotational speeds of stars in several spiral galaxies. They found that stars in the outer regions were moving much faster than expected. Instead of slowing down, the rotational velocities remained roughly constant across a wide range of distances from the galactic center. These flat rotation curves contradicted predictions based on visible stars, gas, and dust alone. The measurements suggested that there was far more mass exerting gravitational influence than what could be seen. This unseen mass extended well beyond the luminous disk of the galaxy, forming a halo that enveloped the visible matter. The implications of these observations were profound. If galaxies contain large amounts of invisible mass, it changes our understanding of their structure and stability. The rapid orbital speeds at the edges of galaxies could not be supported by the gravitational pull of stars and gas alone. Without an additional source of mass, outer stars would escape the galaxy's gravitational hold over time. The presence of an extended dark matter halo provides the necessary gravitational binding to maintain the integrity of the galaxy. This halo is diffuse, not concentrated in the core, and contributes significantly to the total mass, sometimes exceeding the mass of visible matter by several times. Galaxy. Rotation curves vary in detail depending on the size, shape, and type of galaxy. Spiral galaxies, with well-defined disks, offer the clearest measurements of rotational speeds. In these systems, stars, gas clouds, and dust rotate in roughly circular orbits, allowing astronomers to trace velocity profiles from the inner bulge to the faint outer edges. Observations show that most spirals exhibit flat or slowly rising rotation curves beyond the luminous regions, indicating the halo's dominant gravitational role. In smaller dwarf galaxies, which contain fewer stars, the effect of dark matter is even more pronounced. Their visible mass is insufficient to explain the motions of stars, implying that dark matter dominates their mass content entirely. The methods used to measure rotational velocities are diverse. Optical spectroscopy allows measurement of the Doppler shift of light from stars or ionized gas. Radio observations trace the 21-centimeter emission from neutral hydrogen gas, which often extends far beyond the visible disk, providing velocity data at large radii. Combining these measurements gives a comprehensive rotation curve for each galaxy. The resulting profiles consistently demonstrate the discrepancy between expected velocities from luminous matter and the observed speeds, reinforcing the conclusion that an unseen mass component is present. Theoretical models of galaxy formation and dynamics incorporate these findings. Mass distribution within a galaxy affects orbital motions, density profiles, and the stability of stellar disks. Models that include only visible matter fail to reproduce the observed rotation curves. Adding a dark matter halo with properties tuned to match observations successfully accounts for the flat rotation profiles. These halos are generally modeled as spherical or slightly oblate structures, extending far beyond the luminous regions. The halo density typically decreases with distance from the center, but even at the outer edges, it contributes enough gravity to sustain high orbital speeds. Rotation curves also reveal variations that provide insight into the interaction between dark and visible matter. In some galaxies, small dips or rises in the curves correspond to the distribution of luminous mass, such as concentrations of stars in spiral arms or dense central bulges. These features suggest that while dark matter dominates overall gravitational influence, ordinary matter still shapes the detailed motion of stars. The combined gravitational potential of visible and dark matter defines the dynamics of the galaxy. Detailed mapping of rotation curves across many galaxies allows astronomers to study correlations between halo properties and visible structures, offering clues to the formation and evolution of galactic systems. The study of rotation curves extends to high redshift galaxies, providing information about dark matter in the early universe. Observations with large telescopes reveal that galaxies formed billions of years ago also display flat or slowly rising rotation curves. This indicates that dark matter was already present during the early stages of galaxy formation, influencing the assembly and evolution of cosmic structures. Comparing rotation curves at different epochs allows researchers to trace how halos grow and how baryonic matter interacts with them over time. These measurements support the concept that dark matter is a persistent and integral component of galaxies throughout cosmic history. Rotation curves are not limited to individual galaxies. They inform our understanding of the broader distribution of matter in the universe. By studying many galaxies in different environments, astronomers observe trends in halo mass, concentration, and shape. Larger galaxies tend to have more massive halos, while smaller systems reveal the dominance of dark matter more clearly. These patterns help constrain models of dark matter particle properties and their influence on structure formation. Rotation curves thus provide a bridge between local galactic dynamics and the large-scale structure of the cosmos, connecting small-scale motion to universal mass distribution. Alternative explanations for flat rotation curves have been proposed, including modifications to gravity, but they generally struggle to reproduce observations across the wide variety of galaxies. The consistency of flat rotation profiles in systems with different sizes, shapes, and environments supports the interpretation that an additional mass component, rather than a change in the laws of gravity, accounts for the observed velocities. Dark matter halos remain the most robust explanation, providing a coherent framework for understanding galactic rotation and mass distribution. The cumulative evidence from rotation curves across thousands of galaxies has made them a cornerstone of observational cosmology and the study of invisible matter. Rotation curves also illustrate the scale of dark matter halos relative to visible matter. While the luminous disk of a spiral galaxy might extend tens of thousands of light years, the dark halo can reach several times that distance. The halo is diffuse but massive, contributing significantly to the galaxy's total gravitational potential. Its mass increases with radius, even beyond the region where stars and gas are concentrated. This extended structure influences not only stellar motion, but also the dynamics of satellite galaxies, globular clusters, and gas clouds, all of which orbit within the halo's gravitational field. Observations of satellite systems confirm that halos are extensive and substantial in mass. The measurement of rotation curves and the interpretation of their flatness is a precise scientific process. Astronomers account for projection effects, inclination angles, interstellar gas, and measurement uncertainties. By modeling these factors, they extract the underlying mass distribution needed to reproduce the observed velocities. Repeated studies of the same galaxy using different methods consistently yield similar rotation profiles, reinforcing confidence in the results. The conclusion is clear. Visible matter alone cannot explain the motion of stars. An invisible gravitationally dominant component is required. This conclusion has shaped the study of galactic dynamics in the search for dark matter across multiple scales and environments. Galaxy clusters are among the largest structures in the universe, containing hundreds to thousands of galaxies bound together by gravity. The total mass of these clusters determines the motion of their member galaxies and the behavior of the hot gas that permeates the space between them. Observations of galaxy clusters reveal that the visible mass of galaxies and hot intracluster gas accounts for only a fraction of the total gravitational influence required to hold the cluster together. The majority of the mass appears to be unseen, consistent with the presence of dark matter. This invisible mass dominates the cluster's gravitational potential, influencing the motions of galaxies, the distribution of gas, and the bending of light passing through the cluster. Gravitational lensing provides a powerful tool to map this unseen mass. When light from a distant object passes near a massive foreground cluster, the gravitational field of the cluster bends the light, distorting and magnifying the background images. This effect can produce arcs, rings, and multiple images of the same source. The extent and shape of these distortions are determined by the distribution of mass in the lensing cluster. By analyzing the lensing patterns, astronomers can reconstruct a map of the total mass, including both visible and dark matter components. Gravitational lensing therefore allows direct measurement of mass distributions independent of assumptions about the motion of galaxies or the behavior of gas. Early studies of clusters using gravitational lensing confirmed that most of the mass is not luminous. In clusters where lensing is observed, the visible galaxies and hot gas contribute only a portion of the total gravitational field required to produce the observed distortions. Lens reconstructions consistently show that dark matter forms a halo surrounding the cluster, extending well beyond the luminous galaxies and gas. The mass distribution inferred from lensing aligns with observations from galaxy motions and X-ray measurements of hot gas, providing multiple lines of evidence for dark matter in clusters. One of the most notable examples is the Bullet Cluster, a system of two colliding galaxy clusters. In this system, X-ray observations reveal the hot gas from each cluster, which interacts and slows during the collision. However, gravitational lensing maps indicate that most of the mass does not coincide with the gas, but instead follows the distribution of galaxies, which pass through with minimal interaction. This separation of mass from visible baryonic matter provides a direct visual demonstration of dark matter's presence and its lack of electromagnetic interaction. The Bullet Cluster remains a key piece of empirical evidence confirming the existence of an unseen mass component in the universe. Galaxy clusters exhibit similar patterns on varying scales. Smaller groups of galaxies show the influence of dark matter in their dynamics and lensing behavior, though the effects are less dramatic than in massive clusters. Across multiple clusters, lensing consistently reveals halos of dark matter enveloping the galaxies, confirming that dark matter dominates the mass budget. These observations indicate that the behavior of clusters is governed by gravity from both visible and invisible matter, with dark matter providing the bulk of the mass that binds the system together and shapes its evolution over time. X-ray observations complement lensing studies by tracing the hot gas in clusters. Gas in galaxy clusters reaches temperatures of tens of millions of degrees, emitting X-rays detectable by modern telescopes. The pressure and distribution of this gas reflect the underlying gravitational potential. Comparing the mass inferred from X-ray measurements with the luminous matter reveals a shortfall, again pointing to a dominant dark matter component. The combination of X-ray and lensing measurements provides a consistent and robust picture of the mass distribution within clusters, reinforcing the conclusion that visible matter alone is insufficient to explain cluster dynamics. The influence of dark matter in clusters extends to their formation and growth. Simulations of cosmic structure show that clusters form where dark matter is densest, creating gravitational wells that attract gas and galaxies. Dark matter halos merge and grow over time, guiding the assembly of larger structures. Observational studies confirm that clusters are not isolated, but embedded in a cosmic web of filaments, where dark matter dominates the gravitational landscape. These filaments channel matter into clusters, shaping their evolution and the distributions of galaxies within them. Gravitational lensing also allows measurement of substructures within clusters. Detailed maps show concentrations of dark matter associated with individual galaxies or groups of galaxies, providing insight into the hierarchical formation of clusters. These substructures influence the motion of member galaxies and the morphology of the lensing signal. Observations indicate that the largest halos are composed of smaller halos embedded within them, reflecting the nested arrangement predicted by simulations of structure formation with dark matter. This layered distribution reveals the complex gravitational interplay between dark and visible matter within clusters. Studies of merging clusters highlight the behavior of dark matter under extreme conditions. In addition to the bullet cluster, other systems show offsets between gas and gravitational mass, confirming that dark matter does not interact strongly with itself or with ordinary matter. These observations constrain models of dark matter, indicating that it behaves as a collisionless fluid on large scales. Understanding the dynamics of dark matter in these high-energy events provides critical insight into its physical properties and its role in cosmic structure. The consistency of cluster observations strengthens the case for dark matter. Lensing maps, galaxy velocities, and X-ray measurements all indicate mass distributions that cannot be explained by luminous matter alone. Clusters serve as laboratories for studying the properties of dark matter at large scales, offering evidence complementary to galactic rotation curves. The correlation between lensing mass and visible structures confirms that dark matter dominates the gravitational potential while remaining largely invisible. Observational campaigns continue to expand the sample of well-mapped clusters, refining estimates of dark matter density, distribution, and structure on a cosmological scale. Through clusters and lensing, the role of dark matter becomes more tangible. Its gravitational influence shapes the motion of galaxies, the distribution of hot gas, and the propagation of light across vast distances. The evidence from these massive systems is clear. A substantial portion of the universe's mass is unseen, interacting primarily through gravity. The study of clusters illuminates both the scale and the behavior of dark matter, connecting the motions of individual galaxies to the larger framework of cosmic structure. This understanding provides a foundation for further exploration into the properties of dark matter and the methods by which it can be detected, simulated, and integrated into models of the universe. The universe began in a hot, dense state, expanding and cooling over billions of years. About 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral atoms. Before this time, photons could not travel freely, scattering off-charged particles. Once neutral atoms formed, photons decoupled from matter, creating a background of radiation that fills the universe. This relic radiation is known as the cosmic microwave background, or CMB. It provides a snapshot of the universe at this early stage. preserving information about its composition, temperature, and density fluctuations. By studying the CMB, scientists can learn about the matter present, including the invisible component now known as dark matter. The CMB exhibits tiny variations in temperature called anisotropies, which reflect slight differences in density in the early universe. These fluctuations represent regions of higher or lower matter concentration. Dark matter, which interacts through gravity but not with light, played a crucial role in amplifying these variations. Its gravitational pull drew ordinary matter into denser regions, allowing structures to grow over time. Without dark matter, the fluctuations in the CMB would have been smaller, and galaxies and clusters might not have formed as they did. Observations of these temperature differences provide a direct measure of the amount and distribution of dark matter in the early cosmos. Missions such as the Wilkinson Microwave Anisotropy Probe, or WMAP, mapped the CMB across the sky with unprecedented precision. The data revealed the angular scale of temperature fluctuations and the statistical patterns that indicate the presence of dark matter. WMAP measurements allowed scientists to calculate the relative amounts of ordinary matter, and dark energy in the universe. Dark matter emerged as a dominant component, accounting for roughly 27% of the total energy matter content. Ordinary matter represented only about 5%. The remaining portion, attributed to dark energy, drives the accelerated expansion of the universe. These measurements confirmed that dark matter was not just a feature of galaxies and clusters, but a fundamental component of the universe from its earliest moments. Following WMAP, the Planck satellite provided even more detailed observations of the CMB. Planck's instruments measured temperature and polarization fluctuations with higher resolution and sensitivity. The data allowed refinement of cosmological parameters and provided tighter constraints on the density and distribution of dark matter. Analyses of the CMB from Planck showed how dark matter shaped the pattern of acoustic peaks, oscillations caused by interactions between radiation and ordinary matter in the early universe. The presence of dark matter affected the relative heights and spacing of these peaks, giving a clear imprint of its influence on early structure formation. The role of dark matter in the early universe extends beyond the CMB. Regions of higher dark matter density acted as gravitational wells, attracting ordinary matter and allowing gas to condense. These initial density enhancements became the seeds for galaxies and clusters. Simulations of cosmic evolution that include dark matter reproduce the large-scale structures observed today, such as filaments, walls, and voids. Without dark matter, the observed cosmic web would not have formed in the time available since the Big Bang. Observational evidence from galaxy surveys confirms that these structures trace the distribution predicted by models that incorporate dark matter, linking early density fluctuations to the present universe. Polarization patterns in the CMB provide additional insight into dark matter. Polarization arises from scattering of photons off electrons in regions of uneven density. Measurements of the E-mode polarization allow determination of the ionization history and density variations, while B-mode polarization, though weaker, contains information about gravitational lensing by large-scale structures, which is influenced by dark matter. These observations complement temperature measurements and provide independent confirmation of dark matter's gravitational role in shaping cosmic structures. Combining temperature and polarization data enhances precision in estimating cosmological parameters, offering a clearer picture of dark matter's footprint. The distribution of dark matter inferred from the CMB aligns with observations of galaxy clusters, lensing, and rotation curves, creating a consistent model across multiple scales. Small fluctuations in the early universe evolved under gravity, forming dense regions where galaxies later emerged. Dark matter's presence accelerated this growth, allowing structures to form more rapidly than would have been possible with ordinary matter alone. The correlation between early universe anisotropies and present day structures reinforces the understanding that dark matter underlies the scaffolding of the cosmos, connecting the largest observable scales with the earliest detectable conditions. Temperature and density data from the CMB also allow estimation of the universe's overall geometry and expansion rate. Dark matter contributes to the total mass energy content, affecting the curvature of space and the growth of density fluctuations over time. Models incorporating dark matter match observed flatness and the pattern of anisotropies, while models without it fail to reproduce the observed features. The precision of these measurements has made the CMB a cornerstone of modern cosmology, providing a benchmark for testing theories of structure formation, particle properties, and gravitational interactions. CMB observations reveal the relationship between dark matter and baryonic matter in the early universe. Ordinary matter interacts with radiation, creating pressure that resists gravitational collapse, while dark matter experiences no such pressure. As a result, dark matter could collapse into potential wells more quickly, providing gravitational scaffolding. Ordinary matter then falls into these wells, forming gas clouds and proto-galaxies. This interplay between dark and visible matter explains the timing and distribution of structure formation. The imprint of dark matter on the CMB provides a direct record of this process, showing how invisible mass guided the growth of observable structures over cosmic time. Studies of the CMB continue to inform the search for dark matter particle candidates. By constraining the amount and distribution of dark matter, CMB data limit the properties of possible particles, such as their mass, interaction cross-section, and thermal behavior in the early universe. These constraints are essential for designing experiments in particle physics and astrophysics. The combination of cosmological observations, such as the CMB, with local measurements of galaxy dynamics and lensing, ensures that models of dark matter remain grounded in empirical evidence, connecting the physics of the early universe to the observable present. The legacy of CMB studies demonstrates the scale at which dark matter influences the universe. From temperature fluctuations of a few parts in 100,000, dark matter determined the sites where galaxies would form, the distribution of clusters, and the overall architecture of the cosmic web. Its gravitational effects left a permanent imprint in the radiation that continues to reach Earth today. By analyzing this radiation, scientists trace the evolution of matter from the primordial universe to the complex structures observed across billions of light years. Dark matter's footprint in the CMB thus provides both a measure of its abundance and a record of its crucial role in shaping the universe. Through the combination of temperature, polarization, and statistical analysis, the cosmic microwave background offers a direct window into dark matter's influence in the earliest observable moments. Observations from WMAP, Planck, and complementary missions confirm that dark matter was present and gravitationally active long before the first stars formed. Its density and distribution set the stage for the subsequent development of galaxies, clusters, and the large-scale structure of the universe. The CMB serves as a foundation for understanding cosmic history, providing evidence that dark matter is not only ubiquitous, but also essential to the formation and evolution of matter in the cosmos. The nature of dark matter remains one of the central questions in physics. While its gravitational effects are clearly observable, the identity of the particles that compose it is unknown. Scientists have proposed several candidates based on theoretical models and the constraints provided by observational data. Among the most studied possibilities are weakly interacting massive particles, known as WIMPs and Axions. Other hypothetical particles, such as sterile neutrinos, have also been considered. Each candidate has unique properties and interactions that influence how it might be detected and how it affects the evolution of cosmic structures. Weakly interacting massive particles are particles with mass similar in scale to ordinary atomic nuclei, but that interact with other matter primarily through the weak nuclear force and gravity. They do not emit, absorb, or scatter light, making them invisible across the electromagnetic spectrum. WIMPs are predicted to be stable over the lifetime of the universe, allowing them to persist from the earliest moments after the Big Bang. Their weak interactions must mean they rarely collide with ordinary matter, which explains why direct detection is difficult. WIMPs are expected to have been produced in large numbers during the hot early universe, leaving behind a relic abundance consistent with the observed density of dark matter today. The properties of WIMPs make them attractive candidates for experimental searches because they are massive and interact weakly. WIMPs could occasionally collide with atomic nuclei, producing detectable signals. Experiments often place detectors deep underground to shield them from cosmic rays and background radiation. By monitoring for rare events where energy is deposited in a detector by a passing WIMP, scientists aim to observe these elusive particles directly. Despite decades of effort, no conclusive detection has yet been reported, but upper limits on interaction strength and mass have been steadily refined. These constraints guide theoretical models and inform future experimental designs. Axions offer an alternative possibility for dark matter. Axions are extremely light particles with masses far below that of ordinary atoms, and they interact even more weakly than WIMPs. They were originally proposed to solve a problem in quantum chromodynamics, the theory of the strong nuclear force. If they exist in sufficient numbers, axions could account for the full dark matter content of the universe. Unlike WIMPs, axions are not expected to collide with nucleus, but may interact with electromagnetic fields under certain conditions. Laboratory searches often use strong magnetic fields to convert axions into detectable photons, a process known as the Primakov effect. These experiments continue to push the limits on possible axion properties and density. Sterile neutrinos represent another class of hypothetical dark matter particles. Unlike ordinary neutrinos, which interact through the weak nuclear force, sterile neutrinos do not interact with normal matter, except through gravity and possibly through mixing with ordinary neutrinos. Their mass is expected to be small, but sufficient to contribute to the dark matter density. If present, sterile neutrinos could decay over extremely long timescales, producing detectable X-ray or gamma-ray signals. Observations of galaxies and clusters constrain their abundance and decay properties, offering indirect evidence that may support or rule out their existence. Sterile neutrinos are particularly interesting because they could also provide solutions to other puzzles in particle physics, linking dark matter to fundamental questions about neutrino mass. Other hypothetical particles have been proposed, though fewer are studied in detail. These include gravitinos, superpartners predicted by supersymmetry, and other exotic candidates from extensions of the Standard Model. Each particle type has different implications for cosmology and structure formation. Some are produced thermally in the early universe, while others may arise from non-thermal mechanisms. The density, velocity distribution, and stability of these particles influence how they clump under gravity and form structures, which can be compared to observational data. This approach allows scientists to evaluate the plausibility of different candidates against the known behavior of galaxies and clusters. Candidate particles differ not only in mass and interaction strength, but also in velocity characteristics. Cold dark matter, which moves slowly compared to the speed of light, allows small-scale structures like galaxies to form early. WIMPs and axions are generally considered cold dark matter candidates. Warm dark matter with intermediate velocities might suppress the formation of smaller structures, while hot dark matter, like ordinary neutrinos, moves rapidly and cannot form bound structures at small scales. Observations of galaxies in the large-scale cosmic web strongly support the cold dark matter model, constraining the types of particles that can account for the observed distribution of mass. Theoretical models predict how these candidate particles behave in the early universe. WIMPs, for instance, would have decoupled from the thermal bath at a specific temperature, leaving a relic density dependent on their interaction cross-section. Axions may have formed through a different mechanism, arising from the dynamics of a scalar field in the early cosmos. Sterile neutrinos might have been produced through oscillations from ordinary neutrinos. Each scenario has implications for how dark matter interacts with ordinary matter, how it clusters, and how its presence can be inferred from astrophysical observations. Comparing these predictions to data allows scientists to test models and eliminate candidates that fail to reproduce the observed universe. Simulations of structure formation provide additional insight into particle properties. WIMPs, being cold and massive, create dense halos that match the observed distribution of galaxies. Axions, depending on mass and behavior, could form coherent structures on larger scales, affecting galaxy rotation and halo density profiles. Sterile neutrinos might lead to smoother, less dense halos at small scales, influencing the formation of dwarf galaxies. Observational comparisons between simulations and real data help constrain the types of particles that can comprise dark matter. The results favor candidates that produce structures consistent with what is seen across a range of environments, from dwarf galaxies to clusters. Laboratory experiments and astrophysical observations complement each other in evaluating candidates. Direct detection efforts focus on collisions or interactions with ordinary matter, while indirect detection searches for decay or annihilation products, such as gamma rays, neutrinos, or electrons. Collider experiments, such as those conducted at high-energy particle accelerators, aim to produce candidate particles under controlled conditions. Each approach narrows the possible properties of dark matter particles, informing both theory and subsequent searches. Despite the lack of confirmed detection, these efforts continue to refine our understanding and define the parameter space for viable candidates. The search for dark matter particles is guided by both theory and observation. Candidates must be consistent with gravitational evidence from galaxies, clusters, and the cosmic microwave background. They must also match cosmological constraints, including the observed abundance of matter, structure formation, and the dynamics of the early universe. These criteria eliminate some possibilities and prioritize others, creating a structured framework for experimental and observational efforts. Over time, this iterative process of hypothesis testing and refinement aims to reveal the identity of the particles that constitute the majority of mass in the universe. The study of WIMPs, axions, sterile neutrinos, and other candidates illustrates the connection between particle physics and cosmology. Particle properties, such as mass, interaction strength, and decay channels, influence the growth of structures and the behavior of galaxies. Observations at multiple scales, from small dwarf galaxies to the cosmic web, constrain these properties and provide indirect evidence of the correct candidate. This interplay between theory and observation ensures that models of dark matter remain grounded in measurable phenomena, linking the microphysics of particles to the large-scale architecture of the universe. Candidate particles also differ in how they cluster under gravity. Cold dark matter, such as WIMPs, forms dense halos that influence galaxy rotation curves and cluster dynamics. Axions may produce large-scale coherence in mass distribution. Sterile neutrinos could result in smoother distributions, affecting small galaxies more than large ones. These differences allow observations of structure on multiple scales to discriminate among candidates. Matching the predicted and observed distributions is a key test for any proposed dark matter particle, reinforcing the connection between microphysical properties and cosmic scale behavior. The investigation of candidate particles is ongoing, combining theoretical modeling, astrophysical observation, and laboratory experimentation. WIMPs, Axions, and sterile neutrinos each provide plausible explanations for the dark matter phenomenon, but none has yet been confirmed. Observational constraints continue to tighten, reducing the range of viable properties and guiding the next generation of experiments. These efforts underscore the persistent challenge of uncovering the fundamental nature of dark matter, while highlighting the progress made in understanding its role in the universe. Understanding the potential composition of dark matter is essential for predicting its interactions, distribution, and influence on cosmic structure. Candidate particles provide a framework for explaining gravitational effects observed in galaxies, clusters, and the cosmic microwave background. They also define targets for direct and indirect detection experiments. By exploring these hypotheses, scientists aim to bridge the gap between observed gravitational phenomena and the underlying particle physics. The study of dark matter composition thus represents a critical intersection of observational cosmology, theoretical physics, and experimental research, guiding the pursuit of one of the most profound questions in modern science. Efforts to detect dark matter particles on Earth focus on observing rare interactions between these invisible particles and ordinary matter. Because dark matter interacts primarily through gravity, and in some theories, through very weak forces, these events are expected to be extremely infrequent. Scientists have designed sensitive detectors to measure the tiny energy deposited when a dark matter particle collides with an atomic nucleus. The challenge lies in distinguishing such rare signals from the constant background of radiation, cosmic rays, and natural radioactivity that could produce similar effects. Sophisticated shielding, low-noise electronics, and careful site selection are essential to maximize sensitivity. Many direct detection experiments are located deep underground. Subterranean laboratories reduce the flux of cosmic rays that continuously bombard the surface. These underground facilities are often located in mines or tunnels, hundreds to thousands of meters below ground. By placing detectors in such shielded environments, scientists minimize background events and increase the likelihood of observing a genuine dark matter interaction. The choice of underground location is complemented by layers of shielding made from lead, copper, or water, which further absorb or deflect unwanted particles and radiation from the surrounding rock and air. Detectors use a variety of materials and technologies to capture potential signals. Some experiments use noble liquids, such as xenon or argon, which produce flashes of light or scintillation when a particle interacts with the atoms. Other detectors employ crystals that generate phonons, vibrations in the lattice, which can be measured with sensitive instruments. Semiconductors such as germanium or silicon are also used to detect tiny amounts of ionization caused by nuclear recoils. The choice of material depends on factors like sensitivity, background rejection, scalability, and the expected properties of dark matter candidates. Many experiments operate in dual detection modes and to reduce false positives. For example, some noble liquid detectors can measure both scintillation light and ionization simultaneously. Comparing these two signals helps distinguish nuclear recoils from interactions caused by background radiation, such as gamma rays or beta particles. Event selection relies on identifying characteristic patterns in the signals, including timing, energy deposition, and spatial distribution. Data analysis often involves statistical methods to separate potential dark matter events from remaining background noise, ensuring that any candidate signal meets stringent confidence criteria. Despite decades of effort, direct detection has yet to produce a confirmed observation of dark matter particles. Experiments have placed increasingly stringent limits on the cross-section or probability that dark matter interacts with ordinary matter. These limits constrain theoretical models, ruling out large regions of parameter space for WIMPs and other candidates. Each new generation of detectors improves sensitivity by increasing mass, reducing background, and refining measurement techniques. The gradual tightening of these limits informs both experimental design and theoretical predictions, guiding future searches toward the regions where signals are most likely to be found. The largest and most sensitive detectors currently in operation use multi-ton targets of liquid xenon. These detectors can observe extremely small energy deposits down to a few kilo-electron volts while suppressing background to unprecedented levels. They operate for extended periods, often years, to accumulate sufficient exposure. Long-term stability, low noise, and careful calibration are critical for ensuring the reliability of results. By measuring the number and distribution of candidate events over time, scientists test whether any observed signal is consistent with expectations from dark matter interactions. Other approaches explore alternative particle candidates. Experiments searching for axions, for example, use strong magnetic fields to convert axions into photons, which can then be detected with sensitive sensors. These experiments often rely on resonant cavities or microwave detection techniques. Sterile neutrino searches may focus on observing decay products, such as X-ray photons, from regions of high dark matter density. Each detection strategy is tailored to the specific predicted properties of the candidate particle, including mass, interaction strength, and expected event rate. Combining results from multiple techniques strengthens confidence in any potential discovery. Direct detection experiments must contend with a variety of background sources. Natural radioactivity in the detector materials, the surrounding rock, and cosmic rays that penetrate underground can mimic the signals expected from dark matter. Careful material selection and purification help reduce internal contamination. Active veto systems, which detect incoming particles before they interact with the main detector, provide additional background rejection. Despite these measures, distinguishing a genuine dark matter event from rare background fluctuations remains a significant challenge, requiring rigorous statistical analysis and verification across multiple experiments. Calibration of detectors is essential to ensure accurate interpretation of signals. Artificial sources such as neutrons, gamma rays, or low-energy photons are used to simulate expected dark matter interactions and verify detector response. These tests determine sensitivity, energy resolution, and detection efficiency. Calibration helps confirm that candidate events match the expected signature of a dark matter particle. Continuous monitoring and adjustment maintain the integrity of the experiment over long timescales, ensuring that data collected is reliable and reproducible. The evolution of direct detection technology has progressed alongside theoretical predictions. As models of dark matter properties have refined, experiments have adapted to target specific mass ranges and interaction strengths. Early detectors focused on simpler designs with smaller target masses, while modern instruments emphasize large-scale, highly shielded arrays with multiple detection channels. Advances in cryogenics, electronics, and material science have enhanced the ability to detect exceedingly rare events, pushing the limits of measurement closer to the predicted interaction rates of WIMPs, Axions, or other candidates. Collaboration and redundancy are common in direct detection research. Multiple experiments using different technologies and materials operate simultaneously in various locations around the world. Consistency between experiments strengthens confidence in results and helps identify systematic errors. Discrepancies are investigated thoroughly, often leading to improvements in design or data analysis. International cooperation facilitates sharing of techniques, materials, and knowledge, accelerating progress in the search for dark matter while ensuring that claims of detection are robust and verified independently. Despite the challenges, direct detection experiments continue to expand sensitivity and explore new regions of parameter space. Next-generation detectors aim to increase target mass, further reduce background, and improve discrimination between signal and noise. These advancements improve the likelihood of observing the rare interactions predicted for dark matter candidates. Success would provide a direct link between theoretical models and laboratory evidence confirming the particle nature of dark matter and enabling further study of its properties, interactions, and role in the universe. The ongoing search for dark matter particles on Earth illustrates the intersection of cosmology, particle physics, and experimental engineering. Detectors must operate with extreme precision in controlled environments, while theoretical guidance informs the regions of parameter space to explore. Observations from galaxies, clusters, and the cosmic microwave background inform expectations for mass, interaction strength, and density. Direct detection experiments attempt to observe these particles locally, bridging the gap between gravitational evidence in the cosmos and particle scale interactions in a laboratory setting. Current results from direct detection experiments set limits on interaction strength and mass ranges for WIMPs, Axions, and other candidates. Although no confirmed detection has yet occurred, the experiments rule out many theoretical possibilities and refine the understanding of dark matter properties. The cumulative data shapes models of particle physics, informs future experimental design, and constrains the expected behavior of dark matter within galaxies, clusters, and the early universe. The gradual narrowing of possibilities represents steady progress in solving one of the most enduring mysteries in physics. Direct detection efforts can complement other methods of studying dark matter, including indirect detection and collider searches. Together, these approaches provide a multi-pronged strategy to uncover the particle nature of dark matter. While indirect detection focuses on decay or annihilation products in space, and colliders attempt to produce dark matter under controlled conditions, direct detection seeks to observe actual interactions with ordinary matter. The combination of these methods offers a comprehensive approach to constraining candidate properties and verifying theoretical predictions, increasing confidence in the search for dark matter, particles. Laboratory searches for dark matter remain a long-term pursuit. The rarity of interactions, the need for extreme sensitivity, and the presence of background events make the task formidable. Nevertheless, technological progress and accumulated knowledge steadily enhance the prospects for discovery. Each experiment, even when producing null results, contributes to a deeper understanding of particle properties and informs subsequent generations of detectors. The cumulative effort represents a global scientific endeavor, aiming to capture and study the elusive particles that govern the majority of the mass in the universe. Indirect detection seeks evidence of dark matter through the particles and radiation it may produce. Certain dark matter candidates, such as WIMPs, could annihilate or decay under specific conditions, releasing gamma rays, neutrinos, or other cosmic particles. These products travel across space and can potentially be observed by instruments sensitive to high-energy phenomena. Unlike direct detection, which aims to measure interactions with nuclei on Earth, indirect detection observes the universe as a natural laboratory, looking for secondary signals that trace the presence of dark matter in galaxies, clusters, and other dense regions. Gamma rays provide one of the primary avenues for indirect detection. These high-energy photons are produced when dark matter particles annihilate or decay, and they propagate through space without being deflected by magnetic fields. Instruments such as the Fermi Large Area Telescope, or Fermi-LAT, monitor the gamma-ray sky with high sensitivity and resolution. Observations focus on regions where dark matter density is expected to be highest, such as the center of the Milky Way, nearby dwarf galaxies, and galaxy clusters. Analyses compare the intensity and spectrum of gamma rays to what would be expected from known astrophysical sources, searching for excess signals that might indicate dark matter interactions. Cosmic rays, including electrons, positrons, protons, and antiprotons, offer another potential signal. Dark matter annihilation or decay could produce these charged particles, which then travel through the galaxy and can be detected by space-based and ground-based instruments. The Alpha Magnetic Spectrometer on the International Space Station, along with other cosmic ray observatories, measures particle fluxes and energy distributions. Observed anomalies, such as an unexpected excess of positrons at certain energies, have prompted investigation into whether dark matter could be responsible, though other astrophysical sources, like pulsars, can also contribute similar signals. Neutrinos provide a complementary probe for dark matter. These nearly massless, weakly interacting particles can pass through entire planets and stars without scattering, carrying information from dense regions where dark matter might accumulate. The Ice Cube Neutrino Observatory in Antarctica uses a cubic kilometer of ice instrumented with optical sensors to detect Cherenkov light produced when high-energy neutrinos interact with the ice. By observing the direction and energy of incoming neutrinos, IceCube searches for patterns consistent with dark matter annihilation in the Sun, Earth, or the galactic center. Neutrino observations are particularly valuable because they are less affected by astrophysical backgrounds and propagate directly from the source. High-energy gamma-ray observatories on the ground, such as HESS, Veritas, and MAGIC, use arrays of telescopes to detect Cherenkov light from gamma-ray-induced particle showers in the atmosphere. These instruments focus on the highest energy range, complementing space-based detectors like Fermilat. Observations target regions of high dark matter density and compare measured spectra to predictions from dark matter models. Combined with cosmic ray and neutrino data, these gamma-ray measurements allow cross-verification and enhance the sensitivity of indirect detection efforts, providing a multi-messenger approach to identifying possible dark matter signals. Analyses of gamma-ray data have highlighted intriguing features in some regions, including excess emission near the center of the Milky Way. While these observations could be explained by dark matter annihilation, alternative astrophysical sources, such as millisecond pulsars or supernova remnants, also contribute gamma rays. Detailed modeling of backgrounds, source populations, and particle physics scenarios is necessary to distinguish potential dark matter signals from conventional sources. The interplay between astrophysical modeling and particle theory is essential to interpret indirect detection data correctly. Dwarf spheroidal galaxies provide particularly clean targets for indirect searches. These small satellite galaxies of the Milky Way have high mass-to-light ratios, meaning they contain large amounts of dark matter relative to visible stars. Their relative lack of gas, star formation, and other gamma-ray sources reduces background contamination, making them ideal laboratories for testing dark matter models. Observations of gamma rays, cosmic rays, and neutrinos from these systems provide constraints on the annihilation cross-section and decay rates of candidate particles, complementing laboratory-based direct detection efforts. Clusters of galaxies also serve as targets for indirect detection. Dense regions of dark matter in clusters can enhance the probability of annihilation, potentially producing detectable gamma rays and cosmic rays. Observations with space-based and ground-based instruments seek diffuse emissions from these extended sources. The combination of cluster mass profiles, predicted dark matter density, and measured signals allows scientists to test theoretical models, verify consistency with other observations, and refine constraints on dark matter particle properties. Multi-wavelength and multi-messenger approaches help distinguish dark matter signals from conventional astrophysical processes. Neutrino observations provide additional verification of potential signals. For example, neutrinos from the Sun could indicate that dark matter particles are captured by the Sun's gravity, accumulate in its core, and annihilate. Detection of excess neutrinos from the Sun or other dense regions would be a strong indirect indicator of dark matter, as few alternative mechanisms can produce similar high-energy neutrino fluxes. Combining neutrino data with gamma-ray and cosmic ray observations allows researchers to build a consistent picture across different channels, increasing the confidence in any potential detection. Indirect detection also contributes to constraining particle properties. The absence of signals in gamma rays, cosmic rays, or neutrinos sets upper limits on annihilation cross-sections, decay rates within particle mass ranges. These constraints refine theoretical models, ruling out regions of parameter space and guiding future experimental and observational efforts. By linking astrophysical measurements to particle physics predictions, indirect detection complements both direct searches and collider experiments, providing a holistic approach to understanding dark matter. Simulations of dark matter annihilation in galaxies and clusters help interpret indirect detection data. Models predict the spatial distribution and intensity of secondary particles for given particle masses and interaction strengths. Comparing simulations with observed signals allows scientists to test hypotheses, evaluate background contributions, and refine the understanding of both astrophysical environments and dark matter properties. This iterative process ensures that indirect detection remains grounded in observational evidence while informing the development of particle theories. The cumulative evidence from indirect detection experiments provides constraints but not yet confirmed signals. Observations from Fermi-Lat, Hess, and IceCube inform theoretical models and guide the design of new instruments with greater sensitivity. Although no definitive detection has occurred, the limits derived from these observations narrow the possibilities for dark matter candidates. They complement direct detection and collider searches, forming a comprehensive approach to uncovering the particle nature of dark matter and its role in cosmic evolution. Indirect detection studies highlight the multi-messenger strategy in modern astrophysics. By combining gamma ray, cosmic ray, and neutrino observations, scientists exploit different propagation properties and backgrounds to improve detection sensitivity. Each channel provides independent constraints, and overlapping results enhance confidence in interpretations. The synergy of multiple observational approaches allows cross-verification, ensuring that potential signals are robust and not the result of statistical fluctuations or instrumental effects. The search for secondary effects of dark matter, decay, or annihilation bridges the gap between cosmology, astrophysics, and particle physics. Observing these signals connects the large-scale distribution of dark matter in galaxies and clusters to the fundamental properties of candidate particles. Constraints from indirect detection influence models of structure formation, guide laboratory searches, and inform the development of future observatories. By studying the universe across multiple messengers, scientists aim to capture indirect evidence of the particles that govern most of the mass in the cosmos. Overall, indirect detection provides an essential complement to direct experiments. While direct detection measures interactions in controlled laboratory settings, indirect detection observes the universe as a natural experiment. Gamma rays, cosmic rays, and neutrinos provide information about the locations, densities, and properties of dark matter in space. Instruments like Fermi-Lat, Hess, and IceCube have expanded the observable parameter space and established limits on possible particle properties. Together, these observations form a critical pillar in the ongoing investigation of dark matter. Some scientists have explored alternatives to dark matter, proposing that the observed gravitational effects might arise from modifications to the laws of gravity rather than from unseen mass. One of the most studied alternatives is modified Newtonian dynamics, or MOND. This framework suggests that Newton's law of gravity or inertia changes at very low accelerations, such as those found at the edges of galaxies. In these regions, the apparent need for dark matter could instead be explained by a different relationship between force and acceleration. MOND aims to reproduce galaxy rotation curves without invoking invisible matter. MOND introduces a characteristic acceleration scale below which gravitational behavior deviates from the classical Newtonian form. In regions with accelerations above this scale, ordinary laws of gravity apply, while below it, the effective gravitational attraction becomes stronger than expected from visible matter alone. This adjustment allows MOND to explain the flat rotation curves of spiral galaxies, where the orbital speed of stars does not decrease with distance from the center as Newtonian gravity would predict. The theory has successfully described many galactic rotation curves, matching observations with minimal free parameters. Other alternative models extend MOND or propose additional modifications to gravity. These include theories that adjust general relativity at large scales, known as relativistic MOND extensions, as well as hybrid models that incorporate both modified gravity and some form of unseen matter. Some theories invoke extra dimensions, scalar fields, or changes to the gravitational constant over cosmic scales. The goal of these approaches is to account for the gravitational phenomena attributed to dark matter, such as galaxy rotation, cluster dynamics, and lensing, while remaining consistent with well established physics in other regimes. Comparisons between MOND and the standard dark matter hypothesis reveal strengths and limitations. MOND often reproduces galaxy scale phenomena with remarkable accuracy, predicting the shapes of rotation curves and correlations between baryonic mass and velocity. It provides a natural explanation for the Tully-Fisher relation, which links the luminosity of a galaxy to its rotational speed. Dark matter models can also reproduce these relations, but typically require careful tuning of halo properties and distribution. The success of MOND on galactic scales demonstrates that alternative gravity models can capture some observed regularities without additional mass. However, MOND and similar theories face challenges at larger scales. Observations of galaxy clusters, gravitational lensing, and the cosmic microwave background show mass discrepancies that MOND alone cannot fully account for. Clusters exhibit gravitational effects far exceeding what can be explained by visible matter under modified gravity, suggesting the presence of additional unseen mass. Similarly, the statistical properties of the cosmic microwave background, such as the relative heights of acoustic peaks, are consistent with dark matter but difficult to reproduce using MOND alone. These constraints indicate that while modified gravity may play a role, it may not eliminate the need for dark matter entirely. Gravitational lensing provides a key observational test for alternative theories. The deflection of light by mass depends on the total gravitational potential, including any contributions from unseen mass or modified laws. Studies of lensing around galaxies and clusters show patterns that are consistent with dark matter halos, but challenging to reconcile with MOND in its simplest form. Relativistic extensions of MOND can reproduce some lensing effects, but they require additional fields or modifications that increase theoretical complexity. The interplay between lensing observations and alternative gravity models highlights the difficulty of fully replacing dark matter with modified laws. Cosmic structure formation offers another critical test. Dark matter models naturally explain the growth of structures from the small density fluctuations observed in the cosmic microwave background. Modified gravity must reproduce the same structures without invoking unseen mass, which proves challenging. Simulations using MOND-like prescriptions can produce some large-scale structures, but often struggle to match the observed distribution of clusters, filaments, and voids. The standard dark matter model remains more consistent with the observed large-scale architecture of the universe, though alternative models continue to be refined and tested. Alternative theories also face constraints from high-velocity galaxy collisions. Systems such as the bullet cluster show a separation between the visible matter, mostly hot gas, and the gravitational potential inferred from lensing. In these cases, modified gravity alone cannot fully explain the offset, suggesting the presence of additional mass that behaves like collisionless matter. These observations represent a significant challenge for MOND and similar models, reinforcing the necessity of some form of unseen mass or particle component, in addition to modified gravitational laws. The comparison between alternative theories and dark matter illustrates the interplay between observation and theory. On galaxy scales, modified gravity provides an elegant description of rotation curves and scaling relations. On cluster and cosmic scales, dark matter offers a consistent framework for structure formation, lensing, and the cosmic microwave background. Each approach has areas of success and limitations, guiding further refinement and testing. Some researchers explore hybrid models, combining modified gravity with a smaller amount of dark matter to reconcile discrepancies across different scales. Precision measurements continue to test these alternatives. Observations of dwarf galaxies, tidal streams, and satellite systems provide detailed gravitational data in low acceleration regimes. These systems are particularly sensitive to deviations from Newtonian dynamics, offering critical tests for MOND. At the same time, surveys of galaxy clusters, gravitational lensing maps, that's in cosmological probes, constrain the mass and distribution of dark matter. The combination of small and large scale tests allows scientists to evaluate alternative gravity theories rigorously, comparing predictions with empirical data at multiple levels. The theoretical development of MOND and other modified gravity models involves balancing simplicity and predictive power. MOND's appeal lies in its ability to reproduce specific galactic observations with minimal assumptions. Extensions and relativistic versions aim to address larger scale phenomena, but they introduce additional parameters and complexity. Each modification must satisfy solar system tests, cosmological observations, and astrophysical constraints simultaneously. These requirements ensure that alternative theories are not only mathematically consistent, but also physically plausible in diverse environments. Despite challenges, alternative gravity models contribute to the understanding of dark matter. They highlight the importance of low acceleration regimes, the relationships between baryonic matter and dynamics, and the predictive success of simple physical rules. Even if dark matter remains the dominant explanation, insights from MOND and similar frameworks guide investigations into the connection between visible and invisible matter. They provide valuable context for interpreting galactic rotation, scaling relations, and the interplay between baryons, and the gravitational potential, enriching the broader study of cosmic structure. Ultimately, alternative theories and modified gravity offer complementary perspectives to the standard dark matter hypothesis. While dark matter explains most observations across multiple scales, alternative models reveal patterns and regularities that merit investigation. Observational tests, including rotation curves, cluster dynamics, lensing, and the cosmic microwave background, continue to provide constraints that refine both approaches. The ongoing dialogue between standard and alternative theories strengthens the overall understanding of gravity, mass distribution, and the unseen components that shape the universe. Dark matter plays a central role in shaping the large-scale structure of the universe. Its gravitational influence dominates over ordinary matter, guiding the formation of galaxies, clusters, filaments, that's in the empty spaces known as voids. In the early universe, small fluctuations in density existed in the nearly uniform plasma. These tiny variations, amplified by gravity, acted as seeds for cosmic structure. Dark matter, because it does not interact with light, began to collapse into clumps before ordinary matter could cool and condense. This early clustering set the stage for the development of galaxies and the cosmic web. Simulations of structure formation demonstrate the importance of dark matter. Computer models that include cold dark matter produce filamentary networks of matter with dense nodes where galaxies and clusters form, connected by thin filaments and separated by voids. These simulations closely match the observed distribution of galaxies in surveys. In contrast, simulations without dark matter fail to reproduce the large-scale structure correctly. Ordinary matter alone, influenced by gravity and pressure, cannot collapse rapidly enough to form the observed filaments and dense clusters within the age of the universe. Dark matter halos serve as the gravitational scaffolding for visible matter. Within these halos, gas can cool and condense to form stars and galaxies. The mass and shape of the halo influence the size, morphology, and dynamics of the galaxies it hosts. More massive halos tend to produce larger galaxies or clusters, while smaller halos host dwarf galaxies or satellite systems. Observations of galaxy rotation curves and velocity dispersions confirm that visible matter resides within these larger, dark matter structures, with the distribution of luminous material tracing the underlying dark matter profile. The interplay between dark matter and baryonic matter shapes galaxy evolution. Dark matter halos provide the gravitational potential necessary for gas to accumulate and form stars. Feedback processes, such as supernova explosions and stellar winds, regulate star formation, but the overall structure is anchored by the halo. Spiral galaxies, elliptical galaxies, and irregular systems all form within halos of varying mass and concentration. The correlation between halo properties and galaxy morphology demonstrates the critical influence of dark matter on the visible universe. Filaments in the cosmic web are composed primarily of dark matter, with galaxies forming along their dense cores. These elongated structures connect massive clusters and define the large-scale pattern of matter. Observations of galaxy positions and velocities, along with gravitational lensing maps, reveal the presence of these dark matter filaments even where few stars exist. The connectivity of halos along filaments facilitates matter flow, mergers, and the assembly of larger structures over billions of years, emphasizing the role of dark matter in orchestrating the evolution of cosmic architecture. Voids, regions with very low density, also provide insight into dark matter's role. The absence of dark matter in these areas limits the formation of galaxies, leaving nearly empty spaces between filaments. The size, shape, and distribution of voids and observations match the predictions from simulations with cold dark matter. These patterns highlight the contrast between dense nodes of dark matter and the nearly empty voids, demonstrating the uneven distribution of matter that arises naturally from gravitational collapse and the initial density fluctuations in the early universe. Simulations comparing different dark matter properties reveal how particle characteristics affect structure. Cold dark matter, moving slowly, allows small-scale structures to form early and cluster into larger systems. Warm or hot dark matter, moving faster, suppresses small structures and delays galaxy formation. The observed abundance of dwarf galaxies, satellite systems, and subhalos supports the cold dark matter paradigm, indicating that the particles are slow-moving and capable of forming structures over a wide range of scales. These results provide indirect constraints on candidate particles' mass and velocity. The density profile of dark matter halos influences the formation and rotation of galaxies. Halos typically have a central region of higher density, known as the cusp, and an extended outer envelope. Gas falling into these potentials experiences compression and heating, while dark matter remains collisionless. The combined dynamics shape galaxy rotation curves, gravitational lensing patterns, and the distribution of stars. Observations confirm that halo mass dominates galaxy dynamics at large radii, while baryons contribute more significantly in central regions, consistent with predictions from simulations. Mergers and interactions between halos drive the hierarchical growth of structure. Small halos merge into larger systems, creating groups, clusters, and superclusters. These processes also influence the formation of elliptical galaxies, central bulges, and extended stellar halos. Dark matter provides the gravitational binding necessary to hold these merged systems together, while stars and gas rearrange within the evolving potential. Observational studies of interacting galaxies and cluster mergers confirm the importance of underlying dark matter in maintaining structural integrity and influencing galaxy evolution. The relation between halo mass and galaxy luminosity is a key observational constraint. Surveys of galaxy populations, and combined with gravitational lensing and dynamical measurements, reveal correlations between the total dark matter content and the visible stellar mass. These relationships inform semi analytical models of galaxy formation, allowing predictions of galaxy properties within halos of different mass. Such models help explain the observed distribution of galaxy sizes, luminosities, and morphologies across the cosmic web, emphasizing the link between dark matter and visible matter. Cosmic simulations also reveal the impact of dark matter on cluster formation. Clusters form at the nodes of the cosmic web, where multiple filaments intersect. The density of dark matter in these nodes facilitates the accumulation of gas, leading to the formation of hot intracluster plasma and hundreds or thousands of galaxies bound within a common halo. Observations of cluster mass distributions using both galaxy velocities and gravitational lensing confirm the presence of massive dark matter structures that dominate the cluster's gravitational potential, shaping the dynamics of member galaxies. The interplay of dark matter with baryonic feedback shapes the evolution of large-scale structures. While gravity draws matter into halos and filaments, energy input from stars and active galactic nuclei influences gas dynamics, star formation, and chemical enrichment. Simulations that combine dark matter dynamics with baryonic processes reproduce the observed distribution of galaxies, clusters, and intergalactic gas. These results demonstrate that the cosmic web emerges from the combination of dark matter scaffolding and the complex physics of ordinary matter within it. Observations of the cosmic microwave background provide initial conditions for simulations of structure formation. Density fluctuations in the early universe, measured with high precision, indicate regions where dark matter begins to collapse and form halos. Tracking the evolution of these fluctuations under gravity reveals the development of filaments, voids, and clusters. The agreement between observed large-scale structures and simulations confirms the critical role of dark matter in guiding the growth of cosmic structure, from early density perturbations to the intricate network of galaxies seen today. Dark matter also influences satellite galaxies and dwarf systems. Smaller halos orbit larger hosts, contributing to the hierarchical buildup of structure. These subhalos affect the dynamics, star formation, and chemical evolution of the satellites they host. Observations of satellite populations, combined with simulations, help map the distribution and concentration of dark matter on small scales. Such studies provide important constraints on the properties of dark matter, including its mass, velocity, and interaction characteristics. Overall, dark matter shapes the universe across all scales. From tiny density fluctuations in the early cosmos to vast clusters and filaments, its gravitational influence dominates structure formation. Visible matter forms within the gravitational wells of dark matter halos, tracing the underlying distribution while contributing additional physical processes. The combination of simulations, observations, and theoretical models demonstrates that dark matter is essential for explaining the arrangement and evolution of galaxies, clusters, and the cosmic web. Despite decades of study, dark matter remains one of the most significant mysteries in physics. Laboratory searches, astrophysical observations, and simulations have advanced understanding but have yet to produce a definitive detection of the particles responsible for the majority of mass in the universe. The challenge lies in the very nature of dark matter. It interacts weakly with ordinary matter and does not emit or absorb light. Detecting it requires highly sensitive instruments, careful isolation from background noise, and long observation times. Each experiment contributes to refining theoretical models and narrowing the properties of candidate particles. Next-generation detectors aim to improve sensitivity and coverage. Large-scale liquid xenon and argon detectors are being expanded to multi-ton volumes. These instruments are designed to reduce background radiation further, measure smaller energy deposits, and extend observation periods. Technological improvements in cryogenics, electronics, and shielding enhance the ability to detect rare interactions. At the same time, smaller, specialized detectors target lower mass particles such as axions or sterile neutrinos using resonant cavities, magnetic fields, or novel semiconductor materials. Together, these complementary approaches increase the likelihood of capturing evidence of dark matter particles. Space based and ground based observatories also continue to advance indirect detection. Gamma ray, cosmic ray, and neutrino observatories are expanding their sensitivity and resolution. New missions aim to observe fainter signals, broader energy ranges, and previously unexplored regions of the sky. Observations of dwarf galaxies, galaxy clusters, and the galactic center provide increasingly detailed measurements of potential dark matter annihilation or decay products. Combining multi-messenger data from these observatories strengthens constraints on candidate particles and helps to distinguish possible signals from conventional astrophysical sources. Open questions remain in both particle physics and cosmology. The nature of dark matter particles, their mass, interaction strength, and stability are still unknown. Questions about the role of dark matter in the early universe, the formation of the first galaxies, and the evolution of large-scale structure continue to motivate research. Observations of unusual galactic dynamics, cluster mergers, and filamentary structures raise questions about the distribution and behavior of dark matter across different scales. Theoretical models must account for these observations while remaining consistent with laboratory constraints and cosmological measurements. Future discoveries have the potential to reshape the understanding of the universe. Direct detection of dark matter particles would confirm the particle nature of the missing mass, allowing precise measurements of mass, interactions, and other properties. Such knowledge would connect laboratory physics to the cosmological behavior of galaxies, clusters, and the cosmic web. It would inform simulations of structure formation, refine models of galaxy evolution, and clarify the role of dark matter in cosmic history. A confirmed detection could also open the door to new physics beyond the standard model, revealing forces or interactions previously unknown. Colliders such as the Large Hadron Collider continue to search for dark matter production in high-energy particle collisions. By creating conditions similar to the early universe, these experiments test whether candidate particles can be produced and detected indirectly. Missing energy, unusual decay channels, or other signatures can indicate the presence of weakly interacting particles. Collider results complement direct and indirect detection, providing an independent means to probe dark matter properties and constrain theoretical models. Coordination between these different methods enhances the robustness of scientific conclusions. Theoretical research explores new ideas beyond established models. Hypothetical particles, variations of supersymmetry, hidden sectors, and alternative forces remain under investigation. Simulations of cosmic evolution continue to test the impact of these models on galaxy formation, halo structure, and large-scale filamentary patterns. As observations grow more precise, theoretical predictions are refined, guiding the design of future experiments. The interplay between theory, simulation, and observation creates a dynamic feedback loop that progressively narrows possibilities and directs attention toward the most promising avenues for discovery. Large-scale surveys provide another avenue for understanding dark matter. Observations of galaxy distributions, gravitational lensing, and cosmic microwave background fluctuations offer indirect insights into the quantity and distribution of dark matter. Instruments such as the Vera C. Rubin Observatory, Euclid, and the James Webb Space Telescope provide high-resolution mapping of galaxies, clusters, and filaments. These observations allow scientists to test the consistency of dark matter models across cosmic scales, revealing patterns in structure formation and mass distribution. The combination of detailed observations and simulations strengthens confidence in theoretical interpretations. Despite ongoing progress, challenges remain. Null results in direct detection experiments require continual improvements in sensitivity and background suppression. Uncertainties in astrophysical modeling make indirect detection complex, as gamma ray, neutrino, and cosmic ray signals may originate from multiple sources. Simulations must accurately incorporate both dark matter and baryonic physics to match observed galaxy properties. These challenges demand careful analysis, technological innovation, and coordination across multiple disciplines to ensure that potential discoveries are valid and reproducible. The future of dark matter research is inherently interdisciplinary. Particle physics, astrophysics, cosmology, and computational science all contribute critical insights. Laboratory experiments provide constraints on particle properties. Observational astronomy measures large scale structure, lensing, and high energy phenomena. Simulations test theoretical models and predict observable consequences. By integrating these approaches, scientists create a comprehensive framework for understanding the invisible mass that dominates the universe. Each line of evidence strengthens and informs the others, building a cohesive understanding of dark matter. Prospects for discovery also include exploration of new particle candidates. Axions, sterile neutrinos, and other weakly interacting particles remain viable options. Advances in detector technology, low noise electronics, and quantum sensors improve the capacity to detect extremely rare interactions. Ongoing experiments aim to probe previously inaccessible mass ranges and interaction strengths. Each null result, while not a detection, constrains theoretical models and guides the design of future searches. Over time, cumulative knowledge may reveal the particle responsible for dark matter and illuminate its role in cosmic evolution. Dark matter research also influences broader cosmology. Understanding the properties and distribution of dark matter is essential for interpreting galaxy formation, cluster dynamics, and the expansion history of the universe. Precise knowledge of dark matter density informs models of dark energy and the evolution of cosmic structures. Observations of high redshift galaxies, large scale surveys, and detailed measurements of the cosmic microwave background provide constraints on the early universe, offering insights into how dark matter shaped the formation of the first stars and galaxies. These connections illustrate the fundamental importance of dark matter to cosmology. Ultimately, the search for dark matter continues to push the boundaries of observation, theory, and experiment. Large-scale projects, both ongoing and planned, aim to capture direct evidence, detect secondary signals, and measure the effects of dark matter on cosmic structures. The potential impact of discovery is profound, linking fundamental particle properties to the architecture of the universe. Confirming the existence and nature of dark matter would provide a crucial piece of the cosmic puzzle, connecting laboratory physics with astronomical observations and enhancing understanding of the forces shaping the cosmos. Progress in the field depends on collaboration and sustained observation. International cooperation enables the sharing of expertise, resources, and data, increasing the efficiency and reliability of experiments. By coordinating direct detection, indirect searches, collider experiments, and astronomical surveys, the scientific community maximizes the probability of discovery. Each line of investigation contributes unique insights, while redundancy across multiple methods ensures that any potential signals are verified. This collaborative approach exemplifies the ongoing effort to uncover one of the most fundamental components of the universe. In summary, dark matter remains a central focus of modern physics and cosmology. Current challenges include its weak interaction, the rarity of detectable events, and the complexity of astrophysical backgrounds. Future prospects involve next-generation detectors, improved observational surveys, and refined theoretical models. The potential for discovery carries implications across multiple scales, from particle physics as to cosmic evolution. As research advances, each step brings the scientific community closer to understanding the nature of the invisible mass that structures the universe, shaping galaxies, clusters, and the cosmic web.